This tutorial is about numerical integration using one-point Gauss quadrature. The difference between Gauss quadrature methods and Newton-Cotes methods is that in case of Gauss quadrature, we don't fix the endpoints of the interval, and they're flexible. Actually, we find other points in the middle of the interval and try to find the integral based on those points. For example, in case of 1 point, we find some point x1 in the middle of a and b interval, and we model our integral as the value of the function at that point times some constant that we need to determine. So for 1 point, when we do the computation for a straight line, we find that the weight of that value, or C1, is just the width of the interval, and the point is the midpoint between A and B. So when we implement the 1 point method, we just follow the same process as we did in the rectangular, trapezoidal, or Simpson 1-3 method. The only thing that changes is the plotting and the for loop. And first, let's look at the for loop. So we have our numerical integral value. We started by 0, initialize it to 0, and then for each interval in the for loop, we find the weight, which is the width of the interval. In this case, it's constant. Of course, we're setting it to 2, but we're still computing it in case we have unequal intervals. Then we find the midpoint between the start and the end of the interval. We find the value of the function at the midpoint. We do the plotting of that, of the points, the endpoints, and the plot. We plot the value of the function at the midpoint, and then we also add C1 times f of x1 into our numerical integral value. So after all of these intervals have been computed or added to the integral, we get the final result, and we also plot the error between the analytical and the numerical result. So one other thing that is different compared to the previous methods is that we instead of plotting the endpoints, we also plot the midpoint as a stem plot. So this is plotted as a green color, so you can see where the value of the function is being used to compute the integral. So once we run this, we again get the our value to be 174 and some error, and you can see that for each interval, this middle point, which is plotted as green line, is the point that was used to compute the value of the integral within this interval. And you can see this is very similar to rectangular method. The only difference is that in case of rectangular method, we use the starting point of each interval to calculate the area under that interval. But in this case, we're using the midpoint. And if you compare this with the rectangular method, you will see that this has better accuracy because of the compensation of the error, because we are subtracting some here, whereas we are adding some here. Whereas in case of simple rectangular method, we were only subtracting. So that kind of positive and negative errors add to minimizing the overall error.